So, hello and welcome back once again. So, today we are going to be doing an EDA analysis, so the exploratory data analysis of the data that we are having. So, we have covered quite some ground when it comes to this end to end analysis. We started with the project scoping. We were able to build the ETL pipeline. Then after that, we were able to integrate the various tools that will enable us to make this project a success, including managing our ETL process using Dagster. So Dagster will be the quarterback when it comes to that. Then we also integrated feature store that is using Fist, which will enable us to manage all the features that we are having, or the features that we will be generating on this project. So Fist or the feature store will enable us to have a central repository where we are going to be storing our features, and also it will enable us to retrieve those features whenever we want to do the predictions. That means when it comes to offline predictions and online predictions, we're able to accomplish that using Fist as the feature store. So once that is done, then the next obvious step will be to start on the EDA process, the exploratory data analysis. Under this segment, the most important thing that we'll be covering, we will be trying to understand the data itself. So what story does this data try to explain uh, when it comes to solving the problem that we're actually tackling? So we're going to do the exploratory analysis, try to mask some patterns and correlations uh, based on the data itself. Then, based on that, we're able to come up with a model that we can use to now do the predictions, spoilage prediction, and also the waste rate predictions. So that's the aftermath of the EDA analysis. So EDA is actually important because it tells us the story about our data, what patterns we can formulate from that. Then with that we're able to build the models. So before we actually start on the west on looking at the data itself and the EDA process, let me show you how we can first get that data. So under my shared, I have this file features. Under features, I have this spoilage. I think I had shown you this one, so I don't need to repeat it again. But this is the file that will enable us to generate all the features that we need. So under the spoilage prediction features, then I think I created the config file. So under the config file features, yeah, under features we have the YAML file. And the YAML file documents or lists all the features that will be required for this model. So essentially, what I was doing, I was pulling the entire all features that we created during the ETL process. So then, because this is an EDA process, then once we are done with the exploratory analysis, we can drop the features that we won't need. That means features that don't add value to the model itself. Then also features that might cause or features that might lead to leakage. So those are some of the things that we'll be looking at when you're looking at the exploratory data analysis. Then once we have discovered the patterns, some correlation analysis, that then once we are done with that, then you can drop the features. Then whatever remains, we'll use that to build the models. So today I will be focusing more on the exploratory data analysis. Then in the next coming day, I will look into the model building. So let's look at the exploratory data analysis. So as usual, the first thing, again, you have to import your data. So let me see. Yeah, you have to import all your dependencies, pandas, numpy, matplotlib, and seaborn. Basically, these are used for plotting the charts. So then there's also another nice library you can use, and that is Plotly. Plotly is also important or a nice tool to use when it comes to visualization, because you are able to you're able to plot interactive visualization. So charts that you can interact with them, scroll over, and then you're able to find you're able to uh, the interactivity part comes when you want to dynamically determine the values and so on. So once when you hover around those charts, you're able to see if you're calculating percentages, you're able to see those percentages when you hover the mouse. So those are some of the things that Plotly can enable you to do. But for Matplotlib, Seaborn, in most cases, the charts will be static. Okay? So once we import the dependencies, then we have to import the data itself. So the once we pull the file, I think it will be stored under the. I think it will be found under the artifacts. So that will be your data. Then you can just pull that data. So in my case, my the data had 90 features. So those are the 90 columns and about almost 100,000 rows. Okay, so you can dot head. This is just to display the top 10 rows within the data itself. So you can see we have the data itself. So one thing that you can do or try to compare this, you can look at the pick like for example this with the record ID, then go back to your initial data set and try to see, did I capture the correct values, or the if my record ID is this, does that mean that this is my product ID, store ID, and so on. So that is one thing that you can actually do to to do some sort of verification when it comes to understanding, did your feature did Feast actually pull the correct value when you are, did it pull the correct features with the correct values when it was doing the merging. So that is something that you can actually check. So this one is just to print the columns. These are the columns and everything. Then the target feature generation. So how do we generate our target feature? So the first one that I did was to create a continuous target for regression model. And for this one, I was determining the waste rate, and that is the units that were wasted divided by the initial quantity. So that is what I used as part of my target variable, especially for the regression. Because for this one, remember, I told you that I was building two models in one. So this one, this this was the regression, but this will be second. So the first one was the categorical creates categorical target for classification using the category percentiles. So the threshold, I'm providing the 83rd percentile. So I'm grouping by the different categories. Then I'm calculating the waste rate. So any waste rate that is above this quantile, I'm going to consider that as um, I will be considering that as, let's say, spoiled. So that will be categorized as one. Then anything that is less than this quantile, then we are going to categorize that as zero. So then that will be the is excess waste. Then that will be the one that will be a classification problem. So anything that is, if anything that is anything greater than, I think anything greater than the threshold, then we categorize that as one. So that means that shipment actually we realize that waste based on that shipment. So that is what this target generation is actually means. So threshold proved by the category, and also the reason as to why I'm grouping by category is that I don't want to place an arbitrary value or arbitrary cut of value. So I want to be specific based on the different categories of products, because within the different products they have they have different conditions that will make that product go to waste or get spoiled. And so to prevent or to stop having an arbitrary value that cuts across the different categories. So you have to try to dig deeper into the different categories, then try to find out uh, let the spoilage rate within each category tell us what cutoff are we going to use. So that is essentially what I'm using here. Then with that, we're able to calculate the threshold. Then we're just applying the threshold to determine the target distribution, the 1 and the 0. 1 meaning this is was so that means that waste rate, I think greater than 83%, we consider that as is excess waste. And then the waste rate less than this 83%, then we consider that as uh, the category, no, not the category, the class will be 0. So that is not a complete wastage. Okay. So then we can calculate the waste percentage. So to describe, just to determine we are using this to determine the distribution of values under that waste rate column. So you can see the mean is about 22%, 22, 23%, with a standard deviation of 0.28, 0.3. Then the minimum value generally, of course, it will be 1. So if it's a negative value, then there's something in the data we have to look into. Then 25%, that is 25%, 50% is the mean. Okay, so this is the 75th percentile, then the maximum generally will be 1. That means 1 means that it was 100% waste rate based on that shipment. Okay, then this group by category and the waste rate, then to describe, so you're able to see now for the different categories, you're able to see the waste rate according to the different categories. So you can see generally for the frozen meals, you can see how it varies. Frozen meals, that means that for the frozen meals, some shipments, entirety of that shipment actually went to waste. Then you can see also for the pharmaceuticals, again you can see that some of those shipments actually went to waste. The others are ranging about 0. So 30% of the entire shipment went to waste. Yeah, so that is basically what you can get from this. Then you can see in terms of the mean, yeah, is it the mean or the median? 25th percentile, I think this is the mean. So the mean, you can see, okay, the mean tends to vary. So there's some variation based on the waste rate. So, okay, so once that's done, this is just columns. Then we can check for the infinite values. So infinite values based on the data itself. So infinite count. So select, then we sum them. Then so this is the infinite count should be greater than 1. So these are the columns where we are getting the infinite value. So one thing that I think that results from this infinite value is the mathematics that we used when we were generating these features. So to alleviate that problem, what I did was that, for example, the formula units wasted divided by the units sold. So if the units sold was 0, that means we didn't sell any units of this particular category. So if the units sold is 0 and we divide that with the units wasted, then we get to an infinite value. And so to avoid that, we just look at that specific column and we look at the maximum value or the 99th percentile and we just do the replacement. So we do the same for the economic leakage index. So waste cost was the revenue. So if we didn't sell any units, that means the revenue will be 0. Then if we divide this by the waste cost, again, it will be an infinite value. Even if you try to divide this uh, with a large decimal place, then you also the value will be huge, and it will break the scale that of the values within that specific column. To avoid that, then you can just, again, instead of dividing by 0, just look for the maximum value. Then you can replace that with the maximum value with that. So that is what I did when it comes to search features. Again, you can take this method, go back to your ETL pipeline, and try to fix this when you're generating this. I think I did that, but this is something that when you're doing this analysis, something that you can also consider. Okay, so finite max lambda economic. So this is, I think this is what yeah. So this is the process that I did. So you finite max, so you just look at the maximum value within that value within that feature column, and you just replace it with that. This is the categorical columns, and then you start with the some EDA is starting the distribution. So distribution by category. So everything pharmaceuticals, meat, ready to eat, bakery produce. So there is no much. They're almost 10,000 in terms of distribution. So we have equal count of each product category. So product category will not matter much when it comes to building a model. Then we have a distribution by category. You can see Northeast accounts for most of the goods, or the goods. This is a distribution by region. So Northeast. So this is where maybe you have the most stores, sales, whatever. It can be perceived like that. The distribution by quality grade. So for the different quality A, B, C, and D. This one, there's some slight variation. So this one can be considered as a feature when you're building the model. Distribution by day of week. So purchases during day of week. Again, you can see it's almost tallying, almost about 14,000 in terms of traffic. Distribution by month, almost the same. This won't be necessary. This won't be necessary when you're building the model. Then distribution, if it's weekend, this one is very important. 0 is during, I think, during the weekday, and 1 is during the weekend. Then if distribution, if its product is promoted, so 0 and 1, so you can see as the distribution based on that. So the findings that category and day of week will be meaningless in the ML models. Yeah, similar. I think that's what I've explained. Then shelf life distribution. So define the features. So the shelf life days remaining at purchase. So days remaining at purchase. When you're buying this, what are the days remaining before this product expire? Days until expiry. Days remaining at purchase. Days until expiry. And I don't know, days remaining at purchase and the days until expiry. These two the same things, eh? It seems so. Then a viable sales window. Okay, so we can do this. So based on this, you can see that all have outliers. Again, I'm using log transformation based on that. Then yeah, there are some outliers based on this. The log scale 2. Log value, box plots. Yeah, so this is the distribution. The distribution of when you're looking at the shelf life distributions. Okay, then this is the spoilage risk features. I think I'm repeating myself. Daily spoilage risk index. Oh, these are different. Triple risk score, supplier risk factor, and the logistics vulnerability index. So these are some of the features that we are creating. So again, if you have seen my ETL process, you're able to gauge how I was generating these features. So again, you can see this is the box plots for that. Temperature and its variations. Again, you can see storage temperature deviation. So other deviations, degree, hour exposure. Again, I was using the log transformation because of the distribution of that data. They were highly skewed, so log transformation can tell us the distribution. No, can try to compress that into a normal distribution so that we're able to infer when it comes to that. This analysis is about demand. Again, you can see. Then waste rate by category. So what's the waste rate by category? So you can see we have the waste rate. So you can just multiply this by 100%. So products that are average wasted by category, so ready to eat meat, pharmaceuticals, and seafoods, they have waste rates about of over 20% compared to the others. Then frozen meals have the least waste rate, slightly over 15%. Then waste rate by product, again, you can see, again, most of the products, top 15 products, generally, so sausage is among, is it frozen meals, huh? Yeah, so these are the waste rate for the top 15 products with the highest waste rates. Again, you can see sandwiches, crab, fresh pasta, biologics, salads. Again, okay. Then the spoilage sensitivity versus the rates. So waste rate versus spoilage sensitivity. Again, you can see. So the finding with this chart is that shows that as spoilage sensitivity increases, the waste rate generally rises as well, increasing from approximately 17% at a sensitivity of zero point 0.3 to over 21% at a sensitivity of 9. So this can be a good feature to note that for waste rate, because you can see as spoilage sensitivity. So that means you're looking at a product and determining its sensitivity to spoilage, comparing that to the waste rate. Then you can see there's some sort of direct correlation. Then a shelf life versus the waste. Um, yeah, you have outliers. So you have extreme outliers. So that means that most products have a very short shelf life. Yeah, the stores definitely that is correct, of under 30 days, but a few extreme outliers last up to 700 days. So yeah, so there's some products that they have longer shelf life. For example, if you're selling shoes and so on, they can stay on the shelves for quite some time. And the other and yeah, there's some products that uh, can you say 1 day? Yeah, so then the log scale, so the log scale spreads the lower value, making it much easier to compare the typical shelf life of both groups. So the suppliers, this again, supplier 216, again, top 15 suppliers. Okay, they, according to suppliers, there's no variation. So almost all have an average waste rate of 20%. So suppliers won't be a nice feature for us to consider. Then again, this one we are looking at the supply score versus waste rate, almost the same. The distribution is almost the same. So again, maybe it's a feature we want to consider. A supply risk factor versus the waste. Yeah. So for the spoiled, you can see the median is about about 2. But for the spoilage, I think they don't have a median. If you don't have a median, what does it mean if you don't have a median in a box plot? Can you look? If you don't have a median in your box plot, uh, mm, constant data, raw data, look at the numbers. No, no, no. Just say it's a software. How do we interpret um, the auto median line? So, definitely there's skewness on one side. Oh, that's why you're not getting the median. So that means that the median is overlapping one of the contracts, either the 50th, 75th, or the 25th. Yeah, that's the reason why definitely there's high skewness when it comes to that. Okay, then the store effects. Then they're just the same. No need to bother about that. Distribution of store waste rates. You can see some average waste rate number of the stores. Again, you're able to see distribution of store waste rates, average waste rates versus. It's not actually a normal distribution. Different stores do have different waste rates. So cold chain and logistics. So average waste rates by temperature abuse. So temperature abuse is that meaning that there was a serious fluctuation in terms of temperature. Then when you compare that to average waste rate, you can see again there is some semblance of as the temperature abuse events increase, so does the average waste rate also increases. So this can be a good feature to consider when building the model. Distribution of hours, again, almost the same for both. The finding distribution hour does not have impact on the waste. Yeah, okay. Then temperature deviation by waste outcome. Then the distribution is also almost the same with uh, also those outliers. Okay, then else then packaging score by waste outcome. Yeah, the median packaging score. So then for zero, I think zero is the one packaging score of about 7. This is one's about 8. So there is a subtle relation between packaging score and if an item got spoiled. Bad packaging often leads to spoiled goods. So you can see one uh, packaging score. So good packaging score means less spoilage. Bad packaging score means higher higher rates of spoilage. Yeah, days since expiry. Okay, so identical distribution, both spoilage 1 and unspoilage 0 items share almost the exact same median of around 6 days. Yeah, 6 7 days, with their middle 50% interquartile range spanning a similarly from roughly 8 to 18 days. 8 to 18 days. Yeah. And different because the two distribution overlap almost perfectly, the number of days remaining until expiry does not appear to be a strong predictor of whether the product will ultimately spoil. Yeah, so that's what we are seeing from that. This one, average waste rate by remaining shelf life, doesn't matter. Average, so 0 to 3, 4 to 7, 8. So it doesn't matter. The waste rates are almost this. So 20%, I think, is the mostly average waste rate. Okay. Demand and inventory. Yeah, so the rest you can just go through. I think this one I can talk about this. So this one we are talking about inventory turnover rate by waste outcome. So high turnover prevents spoilage. So non-spoilage products 0. I think this one, yeah, this one have a significantly higher inventory turnover rate with a median cluster at the maximum 10. Yep. Okay. Then the lower turnover correlates with waste. So spoiled products, that means 1, show a noticeably lower turnover rate. So that means that the slower moving inventory is much more vulnerable to spoiling, which is the case because if the products are not moving as fast as we intend them to do, then definitely we are going to have spoilage. So that means for such products, Again, now what I was saying, build a second model for demand. Then we can offer markdown for such products so that instead of them getting spoiled, we can sell them to clear them out. So this one we are comparing unsold stock ratio by waste outcome. So if the products are unsold, what is the waste rate? So low unsold ratio is a safe stock. That means non-spoiled items are zero. Maintain a very low unsold stock ratio with the median sitting about 0.0. Yeah, this one. This indicates that almost all of the inventory was successfully sold. That means that if you sell everything, then we are not getting things. We are not. If you sell everything, then the spoilage rates are lower. Higher unsold ratio in spoiled stock. Spoiled items, this one, show a much higher unsold stock ratio. The median roughly 0.45. This highlights a clear relationship between excess unsold inventory and eventual product spoilage. So if it's just the converse of the other one, if you're not selling this product, then there's a higher chance that they will get spoiled. Then here, looking at the stock depletion rate by waste outcome. Active movement in non-spoiled items 0 display a wide range of stock depletion rates with a median of 1.65, indicating healthy and active inventory movement. But for the spoiled one, they show a stock depletion rate of virtually 0. This indicates that inventory which completely stagnates and fails to deplete almost entirely results in spoilage. That means if you're not selling this product, it will spoil on our shelves. Okay, so that means that you can now see why we should be doing our ED analysis. It tries to paint that picture. And then based on this, if you try to apply this in a logical sense, again, you can see that it almost satisfies what we see ideally. If you're not selling your products, then definitely they're going to get spoiled. Then demand versus unsold stock. There's no clear correlation. Critical 0.3 threshold. Spoilage is the blue dots. Is almost entirely absent below an unsold. Yeah, so you can just read through and find out the finding. Promotions and pricing. There's no much correlation. Waste rate markdown applied versus not applied. For the markdown applied, the waste rates were quite lower. Then markdown applied, then the waste rates were quite higher. And again, the median is closer to the 5th percentile. Then this one, there's no much change. Yeah, so this is discount percent versus waste. There's no much correlation here. Financial impact. Okay, so this was essentially my EDA. Though you can add some if you actually want, but again, you need to understand that EDA is very important. This wasn't really my my main area of focus, because my main area of focus was to build a model, create the container image, then try to push this to a Kubernetes cluster where we can orchestrate this model. So essentially, that was my main intention. So EDA was not something that I wanted to focus more on. But again, in a real scenario, when you're building these models, you have to focus more on the EDA, because the exploratory data analysis tries to tell us a story about our data. What are the underlying patterns that we need to look into? Then once we look into these underlying patterns, are we able to build a predictive model based on that? So you're able to analyze what are factors are correlating with each other, factors that show that factors that or features that show multi-collinearity. You can drop those features. So there's quite intense work that can be done when it comes to the exploratory data analysis. But for my case, again, this wasn't really my focus. That's why you can look into this, then see how I try to achieve this, the explanation that I was able to get from that, and so on. So again, so that's it. So that's it when it comes to the EDA. So I'll also share with you this so that you can also go through, try to add other uh, uh, analysis that you might find. Then from there, I think in the next session we're going to continue with start with the feature engineering. Then we head into building the models and so on. So that's it. That's it from me today. Thank you for your attention. Thank you for your time. Let's meet in the next session where we are going to start on building the models itself. So training the models, training and evaluating the models. That will be the next session. So until next time, see you.